Cool. So today, we're continuing on from yesterday, and the objective today is to understand problem-solving techniques using computing mathematics. Sorry, why is it? Can you guys see my screen, by the way?
Yes, it's clear.
Okay, cool. 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 So problem solving lies at the heart of computer science, and mathematics plays a pivotal role in developing techniques that allow computers to solve problems efficiently and accurately. Mathematical reasoning models and algorithms are essential tools in transforming complex real-world problems into structured, logical solutions executable by computers. Understanding these techniques enables professionals to design systems that are not only effective but also scalable and reliable. Algorithmic thinking. Algorithmic thinking refers to the step-by-step method of solving a problem using a defined set of rules or instructions. This concept is rooted in mathematics and involves breaking down a problem into smaller components, identifying patterns, and creating. Yes. Sorry?
I can see what you are reading.
Can you not see it?
Yes.
Okay, sorry, give me 2 seconds. Check. Share my screen.
I'm sorry, Mr. Hamza. I saw the screen, but I couldn't see what you were reading as well.
Okay. Can you guys see it now on my screen?
I can see your screen, but not the what
No.
you have been.
Now
Yeah,
can you,
yeah. Now it's clear. Yeah.
Okay, cool. Sorry about that. So I'll start again. So algorithmic thinking refers to the step-by-step method of solving a problem using a defined set of rules or instructions. This concept is rooted in mathematics and involves breaking down a problem into smaller components, identifying patterns, and creating logical procedures. Every computer program is built upon algorithms, and understanding how to construct and analyze these algorithms is a core computing skills. For example, sorting data, for e.g. alphabetically or numerically, can be achieved through algorithms such as bubble sort, quick sort, or merge sort. These algorithms use mathematical logic to compare elements, arrange them in a desired order, and optimize performance based on the size and nature of the data set. So basically, algorithms are pieces of code. For example, how it's listed how to sort data. So there's three types of algorithms: bubble sort, quick sort, and merge sort. These are quite known in the computing world, and these are used obviously and quite self-explanatory to sort data. But it's really important to know the concept of algorithms when studying computing and when practically using it. So flowcharts and pseudocode are visual and textual tools used to map out the logic of a problem before coding it. These tools are grounded in logical and mathematical thinking. Flowcharts use geometric symbols to represent operations, decisions, and data flow, while pseudocode expresses logical steps in a simplified human readable form. For example, a flowchart may represent a decision-making process for a logging system, using Boolean logic to determine whether to grant or deny access based on input credentials. Now, I don't know how much experience you guys have with flowcharts, but there's quite a lot of applications that you can create these flowcharts on, and each shape has a meaning in the flowchart. So there's a diamond shape, there's an oval shape, and so on, which we will go into further details later on. Mathematical modeling involves using equations or formulas to represent real-world problems. This is particularly useful in computing fields such as data science, simulations, and financial software. Modeling allows programmers to input variables, apply formula, and predict outcomes. For example, in a business application, profit can be modeled using the formula profit equals revenue minus expenses. Such formulas can be programmed into systems to automatically calculate profits based on user inputs, enabling accurate and instant financial forecasting. Problem solving in computing often involves managing and accessing data sets. Mathematical algorithms are used to search for specific data points or to organize data in an efficient way. Searching algorithms include linear search and binary search, while sorting algorithms include insertion sort, selection sort, and quick sort. Binary search, for instance, is more efficient than linear search for sorted data sets because it uses a divide and conquer approach, halving the search area with each comparison, reducing the time complexity from O(n) to O log n. So this refers back to what we studied yesterday about the big O notation, and we'll go more into that again. Mathematical problem solving also involves recognizing patterns and using abstraction to simplify problems. In programming, pattern recognition helps in creating reusable functions or classes, while abstraction involves focusing only on the relevant data and ignoring irrelevant details. For instance, in a customer database system, abstraction might involve working with just customer IDs and purchase history, rather than the entire data set of contact details, preferences, and feedback. Computers solve problems by making decisions using logical operators such as and, or, and not. Logic is fundamental in flow control structures, for example, if, else, and while loops, and in evaluating whether certain conditions are met before taking action. This is directly tied to Boolean mathematics, a branch that is essential for defining binary decision-making processes. In real-world applications, a logistics company might use logic to determine the fastest delivery route based on weather, distance, and traffic conditions. Here's a summary table of mathematical problem-solving techniques in computing. So algorithmic thinking, the foundations of mathematics here used are discrete mathematics and logic. And an example of real world is sorting customer records using quicksort. Flowcharts and pseudocode uses logical reasoning, and an example could be designing logic in authentication logic. Mathematical modeling uses algebra and arithmetic, and an example could be calculating profit in accounting software. Searching and sorting algorithm could use a foundation of algebra and complexity analysis. And an example could be efficiently locating data in a database using binary search. Pattern recognition and abstraction uses set theory and logic, reusing code module across different software functions is an example. And finally, logic and decision making uses Boolean algebra, controlling flow in software based on user input and system state could be an example. So in an e-commerce website like eBay or Amazon, multiple problem-solving techniques based on mathematics are used. Searching for users search for items using keywords. The system uses search algorithms and pattern recognition to display relevant results. Sorting. Results are sorted by price, relevance, or popularity using sorting algorithms. Modeling. Discounts, tax, and shipping costs are calculated using mathematical formulas. Decision making logic is used to determine if a user qualifies for free shipping or a promotional offer. Abstraction. User preferences are abstracted into profiles to personalize recommendations. Each of these processes is a mathematical solution applied through computing to address real-world problems efficiently. The conclusion here is that mathematics provides the essential tools and techniques required for effective problem solving in computing. Whether designing algorithms, managing data, or modeling real-world scenarios, mathematical thinking enables accuracy, reliability, and innovation. As technology advances, problem solving using computing mathematics becomes even more crucial across all sectors, from e-commerce and healthcare to engineering and artificial intelligence. Therefore, the ability to apply mathematical methods to solve complex problems is a key skill for any computing professional. So, describe approaches to problem solving. Problem solving is an essential skill in computing involving the use of structured method to identify, analyze, and resolve issues. A systematic approach allows computing professionals to address challenges effectively, whether in software development, data analysis, system design, or user experience. Understanding the different problem-solving approaches used in computing is vital for creating logical, efficient, and innovative solutions. Several approaches to problem solving are widely used in computing and supported by mathematical reasoning. These include the top-down approach, also known as stepwise refinement. This involves breaking a large problem into smaller, more manageable sub-problems. Each component is tackled individually, often starting from the most general aspect of the problem and moving towards specific details. In software development, creating an online shopping system can be broken down into user registration, product browsing, shopping cart management, and payment processing. Benefits of this can be that it simplifies complex problems, enhances clarity and structure, and promotes modular programming and code reusability. Now, talking about your assessment and assignment, this will be quite important to know the benefits. So it's quite important to note this down. Now, this approach starts by solving the simplest or most fundamental components first, and then combining them to build the full solution. It is commonly used in object-oriented programming, where individual objects or modules are created and then assembled into larger systems. An example is that in a web application, developers may start by code reusable components like buttons, input fields, and login modules, which are then integrated into a full interface. The benefits of this that it promotes reuse of tested modules, it encourages incremental development, and it also reduces the risk of critical failure at higher levels. Divide and conquer. This method involves recursively breaking a problem into smaller subproblems, solving each independently, and then combining the results. It is especially useful in algorithms such as quicksort and merge sort. An example, in a sorting algorithm, the list is divided into halves. Each half is sorted and then merged. The benefits of this is that it increases efficiency in large data sets, parallelizable for high performance computing, and simplifies complex mathematical operations. Brute force. This method attempts to every possible solution until the correct one is found. While often inefficient, it can be used when the problem space is small or when no better algorithm is known. An example in password cracking, a brute force attack tries every possible combination until access is gained. This guarantees a solution is simple to implement and useful as a baseline for testing optimized solutions. Heuristics involves using practical techniques or rules of thumb to find satisfactory solutions quickly. While they do not guarantee an optimal answer, they are often used when time or computational resources are limited. In AI pathfinding, the A-star algorithm uses a heuristic function to find a good path without exploring all possible options. The benefits are that it's fast and resource efficient, suitable for real-time systems, useful when exact solutions are impractical. Trial and error involves testing different solutions until one works. Although inefficient, it is commonly used in prototyping and user interface design where user feedback guides the refinement of solutions. For example, in game development, adjusting parameters, e.g. speed and gravity, through testing until the right user experience is achieved. The benefits of this is that it encourages experimentation, effective in exploratory design tasks, and helps uncover unforeseen issues. Though the mathematical and analytical approach involves modeling a program using mathematical formulas and applying logical or algebraic method to derive a solution. It is used in system analysis, data processing, and algorithm development. An example is optimizing delivery routes using linear programming models in logistics software. The benefits of this is that it produces precise measurable results, ideal for optimization and prediction, and well suited to automated computation. The summary table of these approaches can be seen here. Obviously, it has the description like I described before, an example of the use of it, building a web platform for top-down approach, feature by feature, and the key benefits, so it enhances modular design and clarity. Bottom-up approach, it solves small components first and integrates them. Then example is developing UI elements before full application, and this promotes reusable components. And so on with the divide and conquer, brute force, heuristic, trial and error, and mathematical and analytical solutions. I'll give you 1 or 2 minutes to just have a look at this and note it down if you need, and then we'll move on.
Move on.
Sorry?
You can continue.
Yeah, I'm gonna. Can I continue? Is that okay?
Yeah.
Okay, cool. No worries. So the conclusion is that effective problem solving in computing relies on selecting the most appropriate approach for a given scenario. Whether using a top-down design for complex software systems, divide and conquer for efficient sorting, or mathematical modeling for optimization, each method offers unique benefits. A strong understanding of these techniques enhances a programmer's ability to approach challenges systematically, efficiently, and creatively. Ultimately, combining these approaches with mathematical principle leads to a more robust, innovative, and scalable solutions across all areas of computing. In computing and problem solving, certain terms have specific meanings that relate to the flow of data, control of processes, and logical reasoning. Understanding terms such as variable, constant, causal factor, and path is essential when designing programs, analyzing systems, or constructing mathematical models. So here's an overview of what a variable is. This is a name, storage, location in a computer program that holds a value which can change during the execution of the program. Variables are fundamental in computing as they allow developers to store data, perform calculations, and control program behavior. Sorry. Variables can store various data types such as integers, floating point numbers, characters, or strings. They act as placeholders for values that may vary depending on input, system state, or user interaction. An example in computing in Python. So as you can see, user age is a variable and its initial is key. Initial value is 25. Now the next part of the code adds one to this age. So the final value of the age will be updated to 26 during the execution of the program. The importance of this is that it allows programs to process dynamic data, support user interaction and input-based logic, and facilitate loop counters and condition checking. And constant is a value that does not change during the execution of a program. Unlike variables, once a constant is defined, its value remains fixed throughout the life of the program. Constants are useful for defining fixed values such as mathematical constant, for example, pi, which is 3.14159, or configuration values such as maximum logging attempts. An example can see in Java. This is how you define a constant is by writing final before the actual condition, before the actual variable. I mean constant. So here the maximum users can be 100, and this will never change because that has been decided for this set of program for the maximum users. Now, this enhances code readability and maintainability, prevents accidental changes to fixed values, useful for defining rules or limits within applications. A causal factor is an element or condition that contributes to the occurrence of a particular outcome or effect. In computing and system analysis, causal factors help identify why a certain event happened, especially when troubleshooting or analyzing faults, performance issues, or unexpected results. An example in computing is in software testing, where if a program crashes whilst when loading a specific file type, the causal factor may be incorrect file handling logic or unsupported file format. This supports in the root cause analysis of system errors. It supports decision making during debugging and optimization, and it assists in risk management and system design by identifying failure triggers. In computing, the term path can refer to different concepts depending on the context. The most common uses are in file systems and control flow or program execution paths. A file path specifies the location of a file or directory within a file system hierarchy. Paths can be absolute or relative. Absolute paths include the full location, for example, see user documents report.txt. Relative paths specify a location relative to the current working directory, for example, ./images/local.png. Execution path in programming. A path also refers to the sequence of statements or decision taken by a program during execution. These paths are determined by control structures such as if-else, switch, and loops. An example in computing could be in this program. For example, if user logged in, show dashboard, which is clearly a function here, else show login screen, which is a different function. So this has two possible execution paths depending on the user login status. Sorry. And this is something that I briefly discussed yesterday, if you remember. Now, the importance of this is that understanding execution paths helps in thorough testing. For example, test all possible paths. File paths ensure correct access to system resources. Path analysis is used in debugging, security analysis, and system navigation. Key terms here are shown that we have discussed about before, including variable, constant, causal factors, and path. So yeah, this is the definition of it, the example used, and also the importance of each of these key terms, which is quite important to note down. I'll give it a minute or so before I move on. Cool.
Yeah, you can.
By the way, should I go back? Is that cool with these?
Yeah.
All right. So the conclusion of this is that understanding the definitions and uses of variables, constants, causal factors, and paths is essential for anyone working in computing. These concepts support logical programming, efficient problem solving, and robust system design, whether managing dynamic data, tracing causes of errors, or navigating execution flows. These terms form a foundation for computing operations and analysis. Root cause analysis is a structured problem-solving method used to identify the underlying causes of faults, defects, or problems in systems. In computing, RCA is commonly used in software development, IT support, cybersecurity, and system maintenance to prevent recurring issues by addressing their core origin rather than merely treating the system symptoms. The object of RCA is to investigate not just what went wrong, but why it went wrong, and to propose corrective actions that will prevent future occurrences. RCA is based on the principle that problems are best solved by removing their root causes, not just fixing the surface level effects. An example scenario is application login failure. The problem is that users are unable to log into a web application. The system displays an invalid credentials error even when the username and password are entered correctly. The observed issue here is that users are repeatedly receiving login errors despite entering correct details. Impact is high because users cannot access their accounts, leading to a loss of trust and potential revenue. So, to gather data and evidence, the application logs indicate repeated failure login attempts. Test accounts using the same credentials also fail. The password input field on the front end correctly collects input. The database stores the password in an encrypted format using SHA-256 hashing. The backend is comparing the hashed user input against the stored values. So the possible cause front-end is sending incorrect data is unlikely because form submission verified by browser dev tools. Server-side validation logic is faulty. This is possible as logic in authentication function may be broken. Hash password don't match stored values. This is likely as the user input hash is not matching the stored hash. Incorrect hashing algorithm used is also possible as a mismatch in hashing methods between systems can occur. By further debugging, developers discovered that the system was previously updated to hash user password using SHA-512, but the login comparison function was still using SHA-256. The root cause is a mismatch between hashing algorithm used for password storage and that used for verification. Develop and implement solutions. Update the login function to use SHA 512 hashing for verification to match stored data. Add automated tests to catch hash mismatches in the future, and update system documentation to reflect the hashing standard used. Verify the effectiveness of the solution. After the fix, users successfully log in and using correct details. No errors found in test cases or error logs after implementation. Incident closed and monitored over the next 7 days to ensure the issue does not reoccur. So summary table of RCA. First, you look at the problem, and in this case, it was users receive invalid login errors with correct credentials. Then you look at the system symptoms, which is the login fails for all users, correct credentials are rejected. Then we look at the evidence. So the log showed mismatched hashes, front end works correctly. The root cause is then found, which is the password verification used a different hashing algorithm than the storage, and the solution was to align both systems to the same hashing standard algorithm. And the preventative action was to implement automated hash validation tests and internal code audit, which will prevent future reoccurrence. Conducting RCA prevents the reoccurrence of costly issues and improves system reliability. In development environments, RCA contributes to improved user satisfaction through faster issue resolution, increased system security and integrity, better documentation and team collaboration, reduction in downtime and maintenance costs. RCA is an essential method for resolving recurring issues in computer systems. By identifying the underlying cause of login failure through methodical steps, developers were able to correct a critical system flaw and prevent further disruptions. Applying RCA improves the robustness and reliability of computer systems, making it a vital skill for IT professionals, software engineers, and support technicians alike. Problem-solving techniques are essential tools in computing, allowing professionals to address challenges in software development, data management, cybersecurity, and system design. By selecting appropriate techniques such as algorithmic thinking, mathematical modeling, debugging, or the divide and conquer method, computing problems can be solved efficiently and accurately. Below are several computing problems and how appropriate techniques were used to solve them. Scenario. So a retail business database system becomes slow when retrieving customer records due to an inefficient sorting method, the bubble sort, being used on large data sets. The technique uses algorithmic thinking and divide and conquer. The solution is that the problem was analyzed and an alternative sorting algorithm was considered. The existing bubble sort algorithm, which is O n squared, was replaced with the merge sort, which is merge sort, which is O n log n. Merge sort uses the divide and conquer strategy to split the list, sort sublists, and then merge them. The outcome was that sorting performance improved significantly, reducing processing time by more than 60% on large data sets. The system can now support larger customer data queries without delay. Problem 2. The scenario was that customers were charged incorrect VAT amounts during online checkout due to a miscalculation in the VAT formula. The method used was mathematical modeling and debugging. The solution was a mathematical model was reviewed. The correct formula was total price equals price plus price times VAT rate. The code was incorrectly applying VAT after discounts. It was corrected to apply VAT before applying discounts. The debugging tools were used to step through the calculation and validate changes. The outcome was that the corrective formula ensures customers were charged the correct amount. User complaints decreased and system trust was restored. The third problem was a dynamic website failed to display the correct user's information after login. This technique was used was flowcharting and variable tracking. The solution was that a flowchart was created to visualize the login and session management processes. It was discovered that the global variable current user was being overwritten by simultaneous sessions. The fix involved changing the session management to be user specific by using unique session IDs. The outcome was that the website now displays the correct information to each logged in user, and the user experience and system reliability has improved. Problem 4. So these are all different scenarios addressing different problems and using different techniques to approach these problems. Problem 4 is an enterprise web application crashed when users uploaded files larger than 10 megabytes. Yeah, megabytes. Yeah, MB. Root cause analysis and trial and error was the technique used. RCA identified memory overflow as the root cause. Through trial and error, developers adjusted the server's maximum file size configuration. Error handling mechanisms were introduced to catch oversized uploads before they reached the server. The outcome was that file uploads are now restricted to 10 megabytes with user alerts rather than the application crashing. No crashes were reported since the fix was implemented. Now, just a little note here that error handling, trial and error, is quite predominant and quite known in the computing world, especially when you get technical and start actually using this in real world examples. So it's a good technique used to overcome some issues. Problem 5 is a scenario where an image recognition model in a machine learning application misclassified over 25% of input images. The technique used to solve this was pattern recognition, statistics, and heuristics. The solution was that the model was retrained using more diverse data. Feature scaling and normalization techniques were applied to the data test. A heuristic adjustment was made by increasing the weight of underrepresented classes during training. Outcome was the classification accuracy improved from 75% to 92%. Model performance stabilized across different image types. So here is an example of what I've spoken about: the problems, the techniques used to overcome them, the solution summaries, and the outcomes. You can have a quick look at it whilst I just get a bottle of water. Give me two minutes. Cool, guys. Is it okay to move on?
Yeah, you can continue.
Thank you. So the conclusion is that problem solving in computing involves applying logical, mathematical, and analytical techniques to address system errors, improve efficiency, and deliver user-friendly solutions. And the examples provided illustrate how different approaches such as algorithmic thinking, mathematical modeling, debugging, and pattern recognition can be successfully applied to a wide range of challenges. By selecting the appropriate method, computing professionals can enhance system performance, reduce downtime, and build reliable and scalable solutions. In computing and data analysis, the appropriate use of constant and variables directly influences the quality, accuracy, and interpretation of data statistics. Constants and variables serve different purposes, but both are essential for storing and manipulating data used in statistical analysis, reporting, and decision making. Understanding how these elements interact with the statistical processes allows computing professionals to design more reliable systems and extract meaningful insights from data sets. Understanding constants and variables in data statistics. A variable is a data item that can change during the execution of a program or data processing operation. It represents dynamic data whose value may vary due to user input, sensor data, time progression, or random generation. A constant, by contrast, holds a fixed value and does not change throughout the program or statistical computation. Constants often represent known parameters such as tax rates, time intervals, or thresholds. In data statistics, variables are essential for measuring patterns, relationships, and variability, whereas constants provide fixed references or control values against which variables are assessed. Variables allow for dynamic data collection, which is essential in statistical analysis. This variability enables the calculation of measures such as mean, median, standard deviation, and correlation. An example, in a temperature monitoring system, the recorded temperature every hour is a variable. Over time, the range of values enables the computation of average temperatures and variance. Statistical analysis often tests the relationship between dependent and independent variables. For instance, in a regression analysis, the independent variable might be the advertising budget, and the dependent variable might be the sales revenue. Without these changing variables, statistical models cannot determine influence or correlation. Variables facilitate the generation of real-time dashboards and data visualization. These inputs change based on live variable values, making them critical for decision-making in business intelligence and system monitoring. Constants define fixed values that serve as standards or control points in data analysis. For example, a tax rate or conversion factor remains unchanged, ensuring statistical consistency. An example of this is a fixed rate of VAT rate of 20% is used to calculate revenue net of tax. This constant must not change during analysis to maintain accuracy. By using constants for standard values, statistical computations remain accurate and reproducible across multiple datasets and timeframes. This is crucial in scientific computing and compliance-based reporting. In experimental data analysis, constants ensure that external factors are held steady, allowing for valid comparisons between varying inputs. An example, in a controlled test of CPU performance, the clock speed is held steady while changing the type of workload. So the clock speed is a constant and the type of workload is variable, ensuring that results are attributed solely to the workload difference. In computing, both constants are variable. Both constants and variables work together to shape how statistical results are computed and interpreted. Misuse of either can lead to incorrect results or misleading statistics. For instance, treating a variable value as constants in a time series dataset may result in underestimating variability and producing incorrect trend lines. Similarly, if constants are accidentally changed during analysis, for example, the tax rate changed midway, the integrity of financial reports may be compromised. Hence, clearly defining and isolating constants from variables is a good practice in statistical computing. Again, here's the table of both variable and constant and the combined use of these, and which shows the function in data statistics, the impact on the analysis, and an example in computing. Evaluation. So understanding how constants and variables affect data statistics is crucial in programming and analytics and data science. Variables are foundation of statistical analysis, offering insight through data changes and trends. Constants, on the other hand, ensure that the analysis is based on stable references, reducing noise and enhancing reliability. For effective data analysis and computing, variables should correctly be defined, validated, and updated. Constants should be clearly labeled, protected from changes, and documented. Statistical models must differentiate between dynamic and static components to provide accurate inputs. Improper use of variables or alteration of constants mid-analysis can lead to misleading statistics and poor decision making. Therefore, a strong grasp of both concepts is necessary for all computing professionals dealing with data. So that's pretty much all of today's lesson. Here are the references and which you can look into some of these books for further reading. And yeah, like I said yesterday, it'll be good to refer to the ebooks and journals on Moodle for this unit. Further reading will be essential to helping you in the assignment. If you've got any queries, questions, either ask me or email the following email, and the submission of the assignment will be done to that email 2 weeks after the completion of the units and the delivery. Thank you for your time, guys. Again, thanks for this week. This is just an introduction, and hopefully from next week it'll get a bit more interesting. If you guys have any questions, let me know. Otherwise, you can sign off for the week. Thanks a lot.
Thank you, Mr. Hamza.
No, thank you.
Thank you. Bye.
Bye.